So today I will speak about the theorem of Birdhouse and Grothendieck about the classification of vector bundle on Riemann surface, on the Riemann field. Then I will talk about further works concerning the classification of vector bundle on compact Riemann surfaces or complex manifold. Maybe not in a chronological order, but possibly in a logical order.
Which is the more difficult one? Which is the more difficult one, the logical order?
So the work of Grothendieck that I will talk about is the following: sur la classification des fibrés holomorphes sur la sphère de Riemann. Then I will talk about the works of Abelian on complex analytic connections in fiber bundles, and on the Krull-Schmidt theorem with application to shift. So I will start with the definition. A Riemann surface for us is a connected one-dimensional complex manifold, i.e. a two-dimensional real smooth manifold with a maximal set of coordinate charts, T alpha from U alpha to R2, such that the change of charts is an invertible holomorphic function from P alpha intersection U alpha U beta to P beta U intersection U alpha U beta for all alpha and beta, and M is connected. Example, this is the Riemann sphere is P1 of C, so I will give this example. P1C is the set of lines of C2 through the origin. This means that we take an n-zero vector in C2 and we take the multiple. So we define P1C as the set of bracket Z0 column Z1. This, in general, we say it is the set with homogeneous coordinate Z0, Z1. On P1C, one has usually, one defines usually the following coordinate patches. U0, it means that we take the points with homogeneous coordinates Z0, Z1, such that the first coordinate is non-zero. And U1 is the set of points with homogeneous coordinates Z0, Z1, such that the second coordinate is non-zero. Then one defines the following two homomorphisms: C0 from U0 to C to a point with homogeneous coordinate Z0, Z1, one associates the quotient. Similarly, we define psi1 from U1 to C to Z0, Z1, one associate the quotient. And on the overlap, we have the chain of charts from C minus 0 to C minus 0, and it is given by Z associate 1 over Z. So this is holomorphic, and P1 of C is a Riemann surface. Similarly, we define a complex manifold of dimension greater or equal to 1, as in the case of Riemann surfaces, but this time we require that the transition functions have to be invertible holomorphic maps from open sets of CM to open sets of CM. Now, given a complex manifold M of dimension M and a complex manifold N of dimension N, a holomorphic map from N to M is a continuous map such that for each coordinate chart Phi alpha from U alpha to Cm on M, and each chart C beta from V beta to Cn on N, such that if the V beta is included in U alpha, we require that the map Phi alpha composed with F composed with C beta minus 1 has to be holomorphic. Now, let us define what a holomorphic line bundle on a Riemann surface is. It is a two-dimensional complex manifold L with a holomorphic projection. So pi is surjective, such that for each M in M, the fiber P minus 1 has the structure of a one-dimensional vector space, and for each M, one has a neighborhood U and a homomorphism Cu, such that this diagram is commutative. In general, one says that we have local triviality. Here, PRU is the projection on U. We also require that CV composed with Cu minus 1 has to have the following form. MW associate GVU applied to MW. So this means that we require that this map is linear in the fiber, and the GVU have to be a non-vanishing holomorphic function. In general, we call the GVU the transition functions, and the CU is called a local trivialization. Example: we take a point P in M, a Riemann surface or a complex manifold. Then we take a neighborhood U0 of P with coordinate chart Z, such that Z of P is 0. And we take U1, which is M minus P, and then we use Z as the transition function to define a line bundle on M. How do we do that? We set Z as the transition function. On the intersection U0, U1, which is U0 minus P, we patch U0 times C and U1 times C by using the map psi, which associate to MW, M G01 MW, and this gives for each point a line bundle which we denote LP, and in general it is called the point bundle associated to P. Now, a holomorphic section of a line bundle L over M is a holomorphic map from M to L such that pi composed with S is identity of M. So in a local trivialization, Cu and Tv of the line bundle L, the section gives Cu of Sm. It is of this form, M Su of M, which belongs to U times C. Similarly, in Tv, we have Tv of Sm. It is M Sv of M, which belongs to V times C. And on the overlap, we have the transition function, which is given by Cv composed with Cu minus 1 applied to MSUM. It gives us this formula. And if we translate it, we get Sv equals the transition function times SU. And this is how one defines in general locally a section of a line bundle. Now, given two sections, we can add them pointwise, and we can multiply a section by a scalar. So the space of all sections of a line bundle is a vector space. Now we have the following theorem. If M is a compact Riemann surface, then the set of sections of L is a finite dimensional vector space. And this follows from Hush theory, for example. I give now examples of sections of line bundle. If we take the line bundle LP that we define, it has a canonical section generally denoted as P. How do we define it? We take two functions Z on U0 that I gave before the definition of U0. It is only a neighborhood of P, and one on U1, which is M minus P. Then we get a section of LP since Z equals Z times 1. So this is a section. Now, let us consider the canonical bundle K, which is a bundle of one forms on a Riemann surface. If we have local coordinates Z and W such that on the overlap, we have W of Z, it is phi beta composed with phi beta minus 1. And it is a function of Z, then dZ and dW will give local trivializations of the canonical bundle. And on the overlap, we have the differential form dW equals dW over dZ times dZ. And this gives transition functions. This gives the transition functions of the canonical line bundle. So let us see what happens in the case of M is P1 of C. We take the usual coordinate patches and we consider the transition functions on the intersection given by G01 of Z equals Z to the power of N. N can be negative or positive. So this defines a line bundle on P1 of C, generally denoted by ON. A section of this line bundle is given by holomorphic function S0, S1 on C, such that on the intersection we have S0 of Z equals Zn, S1 of tilde Z, where tilde is 1 over Z on the overlap. Now we expand S0 and S1 in a holomorphic function by using Z tilde equals Z to the power of minus 1. Then we obtain this relation, the sum over M of AM Zm equals Zn, the sum over M, AM tilde, Z to the power minus M. And when we equate coefficients, we get A tilde M equals AM equals 0 when M is strictly greater than N. And in the remaining cases, we get these relations. So this says that the section is given by a polynomial of degree smaller or equal to N, which is of this form. And hence the dimension of the space of sections of ON is n plus 1. Now I give operations on line bundle. Given a line bundle L, we can associate to it its dual, and it has transition functions. G alpha beta of the dual, it is the inverse of the transition function of L. Given two line bundles, we can take the tensor product, which has transition functions. G alpha beta of the tensor product is the product of the transition function. Now, given two line bundles, we can take the homomorphism between L and L2. And by definition, it is the tensor product of the dual times L2. And the sections of homomorphism from L to L2 are by definition the holomorphic homomorphisms from L to L2. If L tilde is equal to L, then we get the trivial line bundle. Now, if we have a section of L and a section of L tilde, then the product, a section S of L and a section S tilde of L tilde, then the product S times S tilde is a section of the tensor product. Now, let us introduce the notion of genus of a compact Riemann surface. By definition, the genus of a compact Riemann surface is the dimension of the space of sections of the canonical line bundle over M. Let us see what happens for M equals P1 of C. A section of the canonical line bundle looks like F0 of Z times dZ on U0 and F1 of Z tilde dZ tilde on U1, where F0 and F1 are holomorphic functions on C. And we require that these forms have to agree on the overlap, and the condition Z tilde equals 1 over Z. This gives, by differentiation, dZ tilde equals minus Z to the power of minus 2 dZ, and F0Z dZ equals minus Z to the power of minus 2 F1 of Z minus 1 dZ. And if we develop and do the same manipulations as we explained before, we get F0 equals F1 equals 0. So the genus of the Riemann sphere is 0. And we know that from curses on surface theory. Besides, we have dZ equals Z minus Z to the power of minus 2 minus dZ. So K is O minus 2. And we introduced before what ON were. Now a remark, if a line bundle has a nowhere vanishing section S, then there is an isomorphism between this line bundle and the trivial line bundle. We just map MU to U SM, and this is an isomorphism. Now we introduce the notion of shift. It is probably well known to everybody. So a sheaf S on a topological space Y associates to each open set U of Y an Abelian group. So we considering sheaves of Abelian group, and the elements of SU are called section over U, and to each inclusion of open set we have a restriction map from SV to SU, such that if we have this double inclusion, then the restriction from SV to SU is equal to the composition of the restriction. And moreover, if we have a section over SU and a section tau over SV, such that we have this condition, which means that the restriction of sigma to U enter V is equal to the restriction of tau to U inter V, then we can, in a sense, glue the section in a unique way. It means that we can find a mu in the section over U union V with which verifies that the restriction of mu to U is equal to sigma, and the restriction of mu to V is equal to tau. And finally, the empty set is sent to the identity, and RU is equal to identity of U. Example of sheaves. If we take a Riemann surface M and we define SU as OM of U, which is the holomorphic functions on U included in M, this is a sheaf. Let us take a Riemann surface, L a line bundle over M, and S defined by OL, which is the sheaf of which is called the sheaf of holomorphic sections of L. How does one define OL of U? It is a collection of functions HI and U intersected with UI, such that we have this relation HI equals Gij Hg on this intersection. And here the UI are trivializing open sets, and Gij are the transition function. And if we take the open set U equals M, we recover the way we define a section of a line bundle. Now let us take the topological space, and we define SU as the locally constant function on U with values on C or D. This is also a sheaf. And finally, if we take a Riemann surface and we define SU as OM times U, which means that we take the nowhere vanishing functions on U with the group operation being multiplicated. This is also a sheaf. Now, given a sheaf, we can construct the Church cohomology of the sheaf with coefficients in S. How does one do this? One takes a locally finite covering of M by open sets, and we define S0 as the direct sum of SU alpha, S1 as this direct sum, etc. And we take CP as the alternating elements of SP, which means that if we take an element of SP and we permute the indices, we have to multiply the section by the signature of the permutation. Now let us define the homomorphism of Abelian groups from nabla from CP to CP plus 1 in this way. Here, F index alpha 0, etc. is a section over this open set. nabla is in general called the boundary operator, and one can verify that nabla composed with nabla is 0. So let us see how this works. For instance, if we take an element of S0, which is C0, it is a family of elements. So we have F equals F alpha indexed by alpha, and every F alpha has to be in SU alpha. The nabla operator, which acts on F, gives us this formula. We take F alpha, we restrict it to U alpha intersected with U beta, and we take F beta, we restrict it to U alpha intersected with U beta. And nabla F equals 0 means exactly that the local sections piece together to give a global section. Now we define the cohomology group with coefficients in S and relative to the covering. It is defined this way. We take the kernel of nabla from CP to CP plus 1, and we divide by the image. Now, this cohomology group is related to the covering, and we define now the cohomology group of M with coefficient in S as the direct limit over the open covered view of M, partially ordered by refinement, which is this formula. What happens that in general, this is incalculable. So how does one get around this? One chooses in practice a so-called good covering view. There is a covering for which the best cohomology P strictly greater than 0 of all finite intersections of open set of the covering is 0. And in this case, we have the cohomology group of M with coefficient in S relative to U is equal to the direct limit. So how does the direct limit appears here? What happens is that if we have a refinement V of U, which means that for any V beta, one can find an alpha such V beta is included in U alpha, and we can define in this way a partial order. Then what happens is that we have a map TUV from the cohomology of S relative to U to the cohomology of S relative to V. And one shows that if we have this order, meaning that W is a refinement of V, which is a refinement of U, then we have this relation. TUW equals to TVW composed with TUV. And this says exactly that UTUV is an inductive system, and we can consider the direct limit. An instance where we can find a good cover is the case of M, a Riemann surface, and we take the covering of M by connected open charge. Then we know that if non-empty, every finite intersection of the U alpha is isomorphic to a non-empty connected open set of C. Now let M be the sheaf of holomorphic functions on M. Then we have the vanishing of the cohomology of we have the vanishing of this cohomology group because we know that from the Bencke-Stein theorem, if we have a non-empty connected non-compact Riemann surface, it is necessarily a Stein manifold. And we know that the sheaf of holomorphic functions OM restricted to this open set has either coherent sheaf. And from the Cartan-B theorem, we know that the higher cohomologies of a coherent sheaf vanish. So in this instance, we have a good an example of a good cover. Now an example, if we take a line bundle with transition functions G alpha beta given by psi alpha composed with psi beta, then we have G alpha beta equals G minus 1, G to the power minus 1 beta alpha. So the family G equals G alpha beta lies in C1 for the sheaf OM of non-vanishing holomorphic functions. Furthermore, we have nabla of G alpha beta equals this formula, and it is identity. So G alpha beta lies in the kernel of nabla, and this defines an element of H1 of M of the sheaf of non-vanishing functions on M. And moreover, one can show that the set of isomorphism classes of line bundles on M is exactly this cohomology group. Now, given a Riemann surface M, and if we take S as the sheaf of holomorphic sections of the line bundle, then we have the vanishing theorem, which says that HP of MS is 0 for P greater than 1, strictly greater than 1. And for S equals C or Z, then we have also the vanishing of this cohomology group. Now let us set H1MOL equals what? Let us set H1MOL equals we set this as a notation equals H1ML. Then we have the third duality theorem. If L is a line bundle on a compact Riemann surface, then H1ML is the space of global sections of the tensor product of the canonical line bundle times the dual of L, and we take the dual. Now, let us start with the exponential exact sequence on a compact Riemann surface. So this is standard. We have, so this is the sheaf Z. This is the sheaf of holomorphic functions on the Riemann surface, and this is the sheaf of non-vanishing holomorphic functions on M. And E2I pi point is given by F maps to exponential 2I pi F. And F is a section of OM. Now we know from homological algebra that if we have an exact sequence of sheaves, this will induce an exact sequence of cohomology groups. And here the first part, V, C, and C times is due to the fact that we have a compact Riemann surface, and so the holomorphic functions on it are constant. Now, since exponential is surjective on C star from this exact sequence, we know that this map is surjective, so necessarily this map is injective. And we also know from the vanishing theorem that H2M OM is 0. So the previous long exact sequence gives us this short exact sequence. And the map, and moreover, we know from Poincaré duality that H2MZ is isomorphic to Z. So this map delta is with values in Z. And we define the degree of the line bundle L as the image. So remember that H1M OM times is the space of line bundles over M. So we take an equivalence class of line bundles and we map it via delta to delta L, and we define it in this way the degree of the line bundle, which is an integer. And by definition, the degree depends only on the isomorphism class of the line bundle. So we have the following properties of the degree. Given two line bundles L and L tilde, the degree of the tensor product is the sum of the degrees. And this means that delta is a homomorphism. The degree of the point bundle LP is equal to 1. And if we take a section, a global section of L, which vanishes at points P1 and P1 to Pn, and with multiplicities M1 to Mn, then the degree of L is the sum of the Mi. How does one see this? We take the section S, then we multiply it by these sections, and this gives us a non-vanishing section of this line bundle. So this line bundle is trivial, and we get L isomorphic to this tensor product. And since the degree is a homomorphism, we get the result. As a corollary, if we have a line bundle of negative degree, necessarily it has no non-trivial vanishing sections. Now let us define what a vector bundle is. We copy the definition of what a line bundle is. We take a rank R vector bundle over Riemann surface M is a complex manifold E of dimension R plus 1 with a holomorphic projection pi from E to M such that the fiber over M is an R-dimensional complex vector space. And we have the local trivialization property. And the transition functions have, in this case, to still be linear in the fiber. But in this case, the map A is from the intersection U inter V to the invertible matrices, the rank R invertible matrices. And as in the case of line bundles, we have the cocycle condition like this way. Now we can do a similar work as we did in the case of line bundles. Given vector bundles, we can construct their direct products. We can also take, we can also construct their tensor product. Given a vector bundle, we can take its dual, and we can also define the determinant of a vector bundle. And with this, we can define the notion of the degree of a vector bundle on a Riemann surface. It is the degree of the line bundle determinant of E. And similarly, as in the case of line bundles, we have the following vanishing function, the vanishing theorem. Now, we also have the third duality for vector bundles on Riemann surfaces. If we have a compact Riemann surface, then H1 of M OE is equal to the dual of the space of global sections of the canonical bundle times times the dual of E. And we also have the Riemann-Roch theorem. If we have a vector bundle on a compact Riemann surface M of genus GM, then we have dimension of H0 ME minus dimension of H1 ME is equal to degree of E time plus rank of E times 1 minus the Genus. So why do we introduce all these facts? It is because in the proof of the Birdhouse-Grothendieck, we need those objects. So this is the theorem of Birdhouse-Grothendieck. We take a rank R holomorphic vector bundle on P1C. Then one can show that E is isomorphic to the direct sum of OA1 plus OAR. And the OAI are the one we introduced before. Furthermore, we have that if OA1 direct sum OAR is equal to OAB1 is equal to OB1 direct sum OA. Normally it is BR, then we have R equals to R prime, and up to reordering, the AI and the BI are equal. So here normally it is BR. It is BR.
We are prime. So
now in here we have AI. Normally here,
last term.
yeah, there is a misprint. So the idea of the proof is the following. When you use it induction on the rank of the vector bundle E, and one shows that for large N, the tensor product En which is equal to E times On, one shows that this tensor product splits, meaning that En is equal to O plus Q, where Q is a vector bundle of rank R minus 1. Then by induction, Q is isomorphic to a direct sum of this form. And one then multiplies by O minus N, and we get this formula. So this is the idea of the proof of the Birdhouse-Grothendieck. So one sees that it is of the formula that of the form that we wanted. Now, a simple corollary of the Birdhouse-Grothendieck. We have the following: if A is trivial, if and only if degree of E is 0, and the space of global sections of E minus 1 is 0. So one direction is E. If E is trivial, it means that E is this direct sum. So determinant of E is O. Then by definition, the degree of E is 0. And we have E minus 1 equals this direct sum. So the space of sections is equal to this direct sum. And it is 0 since the line bundle O minus 1 has negative degree, so its space of section is 0. Conversely, if we take conversely by the Birdhouse-Grothendieck theorem, we know that E is of this form, direct sum of OAI with AI in Z. And furthermore, we know that the degree of E is A1 plus if A1, it is the sum from A1 to AR. And also we have this relation, the space of section of E minus 1 is this direct sum. And this, so we know that this space of section has to be 0, and this gives that AI minus 1 is strictly negative. So one can see the inequality AI minus 1 strictly negative by, for example, using the Riemann-Roch. Finally, since we have the sum of AI, the sum over I of AI is 0, and AI is negative or equal to 0, then necessarily all the AI are 0, and we have E isomorphic to the direct sum of O. So it is trivial. Now, I introduce briefly further works in the theme of the Grothendieck Birdhouse. In the spirit of the Birdhouse-Grothendieck, we take a holomorphic vector bundle of rank R over a Riemann surface. A subbundle F of E is a collection of vector spaces Fx of the fibers Ex, such that F is a submanifold of E. And this means that we have these technical conditions. Now, definition, another holomorphic vector bundle on a connected complex manifold is called indecomposable if it is not the direct sum of two non-zero subbundles. And we have the ideal crude Remark-Schmidt, which says that if we have a holomorphic vector bundle on a connected complex manifold, we said that every holomorphic vector bundle on a connected compact manifold M is a direct sum of indecomposable subbundles. And furthermore, if we have E1 to EM and F1 to Fn, which are indecomposable holomorphic vector bundles on M, such that the direct sum of the EI is isomorphic to the direct sum of the Fj, then necessarily we have M equals N, and up to permutation of indices, we have E1, EM are isomorphic to F1, Fn. So this is in a sense similar to the statement of the Birdhouse-Grothendieck. So I use the notion of homomorphism between vector bundles. It means only that we have a commutative diagram like this with phi, the projection from E to M, and phi prime, the projection from E prime to M. Now, this is maybe further reading. Historically, the first classification of vector bundles on complex manifold were done by Appel and Humbert, and they classified line bundles on complex torus, which means that we take CG and we quotient by a lattice of CG, which is a the Z module generated by a basis of an R basis of CG. And they show that the space of line bundles over X is isomorphic to the group cohomology. This is the modern statement. So it is isomorphic to the group cohomology H1 of the fundamental group with values and the space of global section of O X tilde times, and X tilde is the universal code. We also had the work of Vale, and Vale he classified vector bundles over compact Riemann surfaces of genus greater or equal to 2, which arise from representations of the fundamental group of the surface. And according to it, such vector bundles arise from a representation of the fundamental group if and only if each of its indecomposable subbundles are of degree 0. And the modern proofs of it use the work of Atiyah on the existence of holomorphic connections on holomorphic vector bundles on complex manifolds. Finally, for the modular aspects of the theory, I refer to Narasimha and Seshadri, Hitchin and Kobayashi, and I think the next speaker is going to talk about moduli spaces. And this morning also, one speaker spoke about moduli spaces, so I will stop here. Thank you for your attention.